All right, so 7.4 starts our introduction into matrices, talks about the definition, which is like the array of numbers, talks about order, and then how to get from augmented matrix to the equation or vice versa. If you look at number 1, if I ask you for the dimensions or order of the matrix, you're counting the number of rows and then the number of columns. So for number 1, what would your answer have been? 1 by 3. And 2? 3 by 2, good. Obviously not test questions, right? But especially you'll see when we get into multiplying matrices, you've got to know the order in order to know if you can multiply them. All right, and then for numbers 3 and 4, it said to write the augmented matrix from the system or write the system from the augmented matrix. So you're either working one way or the other. For number 3, remember your x's, then your y's, then your z's, then the last would be the numbers. So this would be 6, -2, -4, and 10. And then 0, 5, 4, and 5. You do want the 0, you want that placeholder there so that you can work with it. And you can have the little dots in between the -4 and the 10 and the 4 and 5, but you don't need them. Okay, just we assume that the last row is after the equals, or the last column, sorry. And then for 4, this would be, God bless you, those would be your constants. This means this is x, this is y, this is z. If there was a 4th row, it'd be w. Don't ask me why. Some mathematician got drunk and decided to rearrange the orders of the letters of the alphabet at some point. Okay, well.
So for matrices, it'd have to be at least 2 columns?
For what?
Because it has to have the equal sign in one of them. Wouldn't it have to have at least 2 columns?
So if you're going from, because there can be a matrix that doesn't necessarily represent a system. A matrix could be a 1 by 1. It could be the number 2. But in order to get a system, like to use matrices to solve a system, yes, you'd need to have those variables. So then this one is 5x. There'd be no y plus 2z equals 3. 6x minus 5y plus 7z equals -10. Good so far? Yes? Easy stuff? Again, this is kind of like the building block of what we're going to do today. None of those will actually be test questions. Sorry. All right, so 7.4 part 2, we are going to learn how to use matrices to solve systems of equations. We're going to learn 2 methods today, and then there's actually one more at the end of the chapter. So by the end, we will have learned elimination, substitution, graphing, the system with 3 variables where you did the new 1, the new 2, and then what we're going to call today is Gauss-Jordan and Gaussian elimination with back substitution. You just want to pay attention to directions. So I'm going to skip forward over the review questions because we didn't do those yesterday. We'll do those tomorrow. And go straight to, I think this is slide 4. Gaussian elimination with back substitution. So the idea behind Gaussian elimination with back substitution is you're going to perform operations on a matrix to get it into row echelon form. So row echelon form, if you remember from yesterday, is your diagonal of 1s, 0s below that diagonal, and then you can have numbers here. That would be row echelon form. So again, diagonal of 1s and then 0s below that diagonal. So we are going to manipulate a matrix by doing the row operations we're allowed to do. Adding them, switching them, multiplying and adding them in order to get it in this format. And then once it's in this format, you can take it from here and make an equation out of this, or system. Right, because this would be x plus 2y plus 3z equals 5. And then y plus 4z equals 6. And then the last one would be z equals 7. And then you're creating your own triangle system, right, that we can solve using back substitution. You with me so far? All right, so that's our goal. The process is what gets jazzy. So we're going to start with just 2 variables. And 2 equations. It says use Gaussian elimination with back substitution. So my goal is to get it as 1, 1, 0, and then there will be a number, and a number. So the very first thing you're going to do is rewrite it in matrix form. 1, 2, 7, 2, 1, 8. So it's not always this way, but more often than not, the easiest thing to do would be to get a, if it wasn't there already, a 1 in this top corner, and then work your way down with the zeros. I'd want a 0 here, and then I'd want a 1 here. So this one already has the 1 in the top corner, which means my first row is good the way it is. If it wasn't, let's say those two are switched, I could simply switch them so that the 1's in the top left corner. Which means the next step is to get this 0 here. So in your head, think of the ways you can alter a matrix. You can either multiply it by something, right? A non-zero number. I can't multiply that by 0 because it would cancel out the entire row. Is there a number I can multiply 2 by to get to 0 other than 0? No, right? The second thing would be to add 2 rows. If I add these 2 rows, do I get a 0 in the place where that 2 is? No, right? The third thing is alter it and then add it. So how could I get that 2 in the bottom to become a 0? Good. So I'm going to multiply the first row by -2. So I'm going to do, you want to keep a habit of doing your notation. -2 times row 1 plus row 2. So I'm going to take this, I'm going to multiply it times -2, and I'd get -2, -4, -14. And then bring down row 2, 2, 1, and 8, and add them. I'd get 0, -3, and -6. So now whatever rows you just involved in your adding, you could replace either one. So I could take this 0, -3, -6, and replace row 1 with it, or row 2 with it. We already said we like row 1 the way it is, so the goal there was to replace row 2. So I'm going to repeat row 1, and I'm going to change row 2 to this new altered row. Now I've got my 1 here, I've got my 0 here. The last thing I need for this is to put a 1 where that -3 is. How do I do that? Widely. So in matrices, we say, not division, we would say multiply by the reciprocal, right? So if we're really dividing by -3, we are multiplying by -1/3. So my R1 is still the same. And then my -1/3 times R2 is 0, 1, 2. So again, goal for Gaussian elimination with back substitution is the diagonal of 1s with the 0 below, which means this is in row echelon form. And then from here, I make my system, x plus 2y equals 7, and y equals 2. And then I work bottom up, so x plus 2 times 2 equals 7, x plus 4 equals 7, and x equals 3. And my solution gets written as a coordinate point 3, 2. Questions so far? Okay, then comes the 3 variables, 3 equations, right? So the first thing I'm going to do is rewrite this in matrix form. This would be 3, -2, 1, 15, -1, 1, 2, -10, 1, -1, -4, and 14. So in Linker, we have this saying that says, go slow to go fast, okay? Which means, like, be careful the first time around, and you may not have to do it a second time around. Imagine rewriting that matrix and leaving off a negative from the very first step. Everything after that will be wrong. So be so very careful when doing these that you're writing them careful, okay? Don't rush through it and make a mistake. Don't skip and do steps in your head. I guarantee that's where people make mistakes. I know you're smart. You don't need to be that smart. Okay, so if my first goal is to get a 1 in this top left corner, what's one way I could do that? Good. You can switch row 1 and row 3. So the notation there is row 1, switch with row 3. And I'd get 1, -1, -4, 14, -1, 1, 2, -10, and 3, -2, 1, and 15. So I've got my 1 in that spot. Next thing I need is a 0 where the -1 is. What's one way I could do that? Add row 1 and row 2. Doesn't mean it's the only way, right? I could also multiply it by 3 and then add it to the bottom one. So if I add row 1 and row 2, now the two equations that are involved, or two rows that are involved in that, I can replace either one with them. But we already said we like row 1 the way it is. Our goal there was to replace row 2. God bless you. So that time, by getting a 0 in the first column, we also got a 0 in the second column. What row would we want that to be in? The third row, right? We want the 2 zeros and a 1 to be in the third row. So I can actually rearrange row 2 and row 3. And I'm back to where I started. I still need a 0 where that 3 is. How can I get that? There's nothing I can multiply the bottom row by to cancel out a 3, right? Which means my only option is the first row. What would I have to multiply the first row by to add it to cancel out with a 3? -3. So -3 row 1 plus row 2. And that, again, can either replace row 1 or row 2, but our goal here was row 2. So row 1 is going to stay as 1, -1, -4, 14. And row 2 becomes 0, 1, 13, -27. And then 0, 0, -2, 4. So now I've got, starts with the 1 at the top, I got the zeros underneath, and by doing so I actually got another 1 here. The last thing I need is for -2 to be a 1. How do I do that? Good. So divide or multiply by the reciprocal. So -1/2 times row 3. And I get 1, -1, -4, 14, 0, 1, 13, -27, 0, 0, 1, -2. Now this is in row echelon form, diagonal of 1, zeros below it. So I could take from here and create my system. And then I created my triangle, right? So now I can use back substitution. This is going to get plugged in here. And then Y and Z get plugged into the top. And it goes X, then Y, then Z. Super fun, right? Time of your life. It's tedious, right? But that's one of the reasons why we like pushed to get a head start last night is I want you to be able to practice this today. I want you to practice it Wednesday. I want you to be able to practice it Thursday. So that by Friday, it's second nature. It's super easy, okay? And there's more than one way to do these. So just because your method is not the same as somebody else's, it doesn't mean it's wrong. The answer should be the same at the end. And with all the extra time you're going to have at the end of your test, just think you're going to be sitting here bored, right? Because you're going to have so much time. You could take that 5, -1, -2 and plug it back in to every single one of those equations and check to make sure it's right. It's got to work for all three. Questions so far? So that's Gaussian elimination with back substitution. Row echelon, back substitution. Second method is Gauss-Jordan elimination. So this one has more work on the matrix end, but less work on the back substitution side. You're going to start the same exact way. Write the augmented matrix in the system of linear equations. Use elementary row operations to rewrite the augmented matrix. This time, you need it in reduced row echelon, which means diagonal of ones, zeros above and below. So the only non-1 or non-zero numbers are going to come from that last column. The good thing is there's no back substitution work once you get there, because what will happen is you'll get something like x. So if it said 1, 0, 0, 1, 0, 1, 0, 2, 0, 0, 1, 3, then my answer from here is x equals 1, y equals 2, and z equals 3. So there's no back substitution at the end, okay? You got to work a little bit more. My advice here is start the same way as you do the first time. Try to get the 1 in that top left corner. Then work your way down with your zeros. And then sometimes it makes sense to get the 1 here. Sometimes it doesn't. After you get that, you want to work your way up with the zeros. And then probably the last thing you want to do is the one that's here, unless it's super easy to get, okay? All right, so let's start with the 2 system. Step 1, write the matrix. -2, 6, -22, 1, 2, -9. What could you do first? Okay. And I get 1, -3, and +11, and then 1, 2, -9. What else could you have done first step? Because that's not the only thing you could do. Switch it. You could switch it too. Okay, either way. So now I've got the 1 here. I want to work my way down. I want to get a 0 where the bottom 1 is. How do I do that? I could do -1 row 1 plus row 2, or row 1 plus a -1 times row 2. Again, doesn't matter which one. Negative row 1 plus row 2. I get -1, 3, -11, 1, 2, -9. Okay, I get 0, 5, -20. And then I'm going to replace, again, you can replace row 1 or row 2, but row 1 was how we liked it. We were trying to work on row 2. So row 1 stays this, row 2, 0, 5, -20. Okay, so now I have 2 goals from here, right? I want to get a 1 here, and I want to get a 0 here. So think about it in which order that's going to be easier to do. If I do the 0 first, I got to multiply the top row by 5, the bottom row by 3, then combine them, right? What's an easy way to make that 5 become a 1? Multiply by 1/5. So sometimes you want to, like, you know, get a little bit of an idea of what would the next step look like if I did that. And so this is definitely easier. Now, if I want to put a 0 where that -3 is, what could I do? Good. 3, row 2 plus row 1. So I get 0, 3, -12, and 1, -3, 11. And I get 1, 0, -1. And that's going to replace row 1. I've got my diagonal of 1s, my 0 above and below, so x is -1, y is -4, and my answer is -1, -4. Now, I know you guys are super smart, and a lot of times you can do things in your head and be fine, okay? A test is not when you want to do that. So, like, while this is not the hardest step to do in your head, like multiply row 2 times 3 and then add it to row 1, people try to do that in their head. That's where mistakes are made. So be really, really careful. Write them out. Give me the notation, especially if you want partial credit on this test. You better show me the notation that got you to that step. If you want credit on the question, obviously you've got to show me the work, because I know these can be done other ways. Questions so far? Right. And then use Gauss-Jordan, 3 variables, 3 equations. So this should look familiar. We already did the first step of this. I'm going to pull in where we left off. So this is the same example as example 3. Okay, and in example 3, we got to actually here. In example 3, we got it to here. Okay. So now the difference between Gauss-Jordan and Gaussian elimination with back substitution is we've got to work our way to get the zeros in those spots. So to get a 0 in this spot, you could have done -13 row 3 plus row 2. So I'm going to do -13 here, 0, 0, -13, 26, plus 0, 1, 13, -27. 0, 1, 0, -1. And then I'm going to replace row 3 with that one. So 1, -1, -4, 14, 0, 1, row 2 with that. 0, -1, and 0, 0, 1, -2. Now I got to get a 0 in either this spot or this spot, okay? This time, like, there's only one row you can get each of those from. So if I want to put a 0 where the -4 is, obviously I can't combine that with row 2. I got to go row 1 with row 3 to get where the -4 is. And then if I want a 0 here, I have to use row 1 and row 2. The order in which you do that doesn't matter, okay? So how many of you did row 3 times 4 and added it to row 1 next? How many of you added row 1 and row 2 to get the 0 where the -1 is? Yeah, okay, so let's do that. So I would do row 1 plus row 2, and I'm going to get a 0 in that second spot. So I'd get 1, 0, -4, and 13. That's my top row. And then I have 0, 1, 0, -1, 0, 0, 1, -2. So that was adding row 1 and row 2, these two. And I got the 1, the 0, the -4, and the 14. And the -1, the 13. Now I got to get a 0 where this guy is, and I can only do that by working with row 3. So I would do 4 times row 3 plus row 1, multiply this times 4, and I get 0, 0, 4, -8, plus 1, 0, -4, 13, and I get 1, 0, 0, 5. That replaces row 1, so I get 1, 0, 0, 5, 0, 1, 0, -1, 0, 0, 1, -2. So now it's in reduced row echelon, and all I can do is grab this column. X is 5, Y is -1, and Z is -2. So same answer, obviously, because it's the same system, just a different method. For homework, I want you to practice both methods, okay? You can even use both on the same one, like get to a certain point like we did, solve it using back substitution, and then continue to solve it using Gauss-Jordan to make sure you get the same answers. On your test, I have to figure out how long it's going to take me to take the test. Most likely, you'll get a choice. So just because of time's sake, you'll probably get a question like this, and it will say solve either using Gaussian elimination with back substitution or Gauss-Jordan, and you can choose between the two. You just got to make sure you're ready to do at least one of those. Okay. And it's definitely going to be a 3 variable, not a 2 variable. Questions on 7-4?